Let's talk about alkalinity, hardness, and equivalent weights. First, I want you to perform an experiment. Look around your house and find two types of water. One could be tap water, like I have here. The other could be bottled water. You could even try like a carbonated water. I've got some deionized water here because we have a deionized water system downstairs. But even like if you happen to have a water filtration system in your house, you could use water from that. So you could also use rainwater or melted snow depending on the season. So place those two types of water into two different containers. I actually find the experiment much easier to do in bottles like these Nalgene's here, but a cup would work. And don't forget to label them. Then find some soap and a dropper. So I've got a dropper like this here. Maybe you can find a dropper with like a medicine bottle. But basically you just need some sort of way to add small consistent amounts of soap to each one of your types of water. So slowly add soap, record how much you add, and between additions shake or stir the water and try to get bubbles to form. Although your two waters may at first appear the same, you know, they're both like clear, they look drinkable, are they? The difference between these waters, if they are different, is their hardness. Hardness is a measurement of how difficult it is to make a lather with soap. In the comments below, let me know what you observed in your experiment. Everyone's observations are going to be different depending on where you live and what water you chose. For example, in Butte, Montana, we have hard water. Much more soap is going to be needed to make a lather with that water than with distilled water. Hardness is mostly due to calcium and magnesium, and we could write a simplified equation defining hardness, pictured here. In this equation, you can see that hardness is an equivalence per liter. Remember those brackets for calcium and magnesium? That's a chemistry notation that means moles per liter. And you can see that I've said that calcium has 2 equivalents per mole and magnesium has 2 equivalents per mole. And if you canceled out the units on the terms on the right, each term would be simplified to the hardness unit of equivalents per liter. That's always a good check with these equations. But what are equivalents? So equivalents are only used with aqueous solutions, and one equivalent is going to react or be replaced by 1 mole of hydrogen ions. When you're determining the equivalence per mole, you can either use the charge of the cation or the number of hydrogen ions that the anion would react with. For an ionic compound, don't double count. Only use the anion or the cation to determine the number of equivalents. Here are some examples. So you can see CO3 2-, which is carbonate, Ca2+, which is calcium, and then the ionic compound formed by the two, which is calcium carbonate. So if we were to look at carbonate, we see that it has a charge of -2. It would react with 2 hydrogen ions, so it's 2 equivalents per mole. The calcium ion has a charge of 2+, so it would also be 2 equivalents per mole. And with calcium carbonate, remember that you only need to use the calcium or the carbonate in there. So you can say about both of those are going to give you 2 equivalents per mole. So calcium carbonate also has 2 equivalents per mole. A similar concept is alkalinity. Alkalinity is a measure of the ability of a solution to resist changes in pH. In fact, you could do a similar experiment with 2 different waters as you did for hardness. Get fresh water, you can add lemon juice or vinegar, which are both acids, and measure the pH with pH paper or probe between acid additions. If you're ambitious, you could use extract from boiled cabbage as a pH indicator. If I were to use my examples of tap water and distilled water, I would find that I need to add much more lemon juice to my tap water than my distilled water to change pH. That's because my tap water has a higher alkalinity. In environmental systems, alkalinity is most often due to carbonate in the water, or carbonate species in the water. Therefore, we will, for the sake of this course, write a simplified alkalinity equation, which you can see here. So alkalinity, measured in equivalents per liter, is going to be the sum of equivalents of bicarbonate, HCO3 minus, carbonate, CO3 minus, and then with the addition of the hydroxide ion minus the hydrogen ion. And you can see here that I've got those brackets indicating moles per liter, and then I've multiplied each one of those ions by their equivalents per mole. And you can see that that lines up with our definition of equivalence, or how to calculate equivalence that I talked about before. So my tap water happens to be high in both hardness and alkalinity because it has calcium carbonate in it. Often in environmental systems, these two measurements are correlated, but remember they're not the same thing. So both hardness and alkalinity can be measured by equivalents per liter, but they might also be measured by milligrams per liter as calcium carbonate. We'll use equivalent weights to convert between those two units. Let's do some examples. So here we have an example dealing with hardness. So we have a hardness concentration of 200 milligrams per liter as calcium carbonate. So that's that weird unit. Okay, of this, 60 milligrams per liter is due to magnesium hardness, and 160 milligrams per liter is due to calcium. And this is very strange, but you will see this reporting magnesium hardness as milligrams per liter as calcium carbonate. So don't let it weird you out too much. Okay, the first thing we want to do is to convert the total hardness to milliequivalents per liter. So related to that milligram, or equivalents per liter, but milliequivalents per liter. So the first thing we'll do is we'll take our total hardness, so this 220 milligrams, and I'm just going to write calcium carbonate here per liter, and we want to get that to milliequivalents per liter. So I'm going to convert our milligrams to grams. So we have 1,000 milligrams in a gram. I'll go ahead and do my accounting here. And then I want to convert to moles. Remember, so equivalence is kind of related to moles, so let's get it into moles. So 1 mole of calcium carbonate is going to be 100 grams, and you can get that by looking at your periodic table. And then remember, calcium carbonate, we could look at either the charge of the calcium, which is 2, or the number of hydrogen ions the carbonate would react with, which is also 2. So it's 2 equivalents per mole of calcium carbonate. And then, so now we're in equivalents. We need to get to milliequivalents. And so that term milli is just like, you know, with equivalents, it's just scientific notation. So it's just like milli anything. So there's going to be 1,000 milliequivalents in an equivalent. Let's go ahead and finish our accounting. Make sure that we've canceled out everything. And yes, in fact, we now have milliequivalents per liter. And if I type that into my calculator twice, I get 4.4 milliequivalents per liter, which is my answer. Okay, what is the mass concentration in milligrams per liter of calcium? So if we go back here, we will see that 160 milligrams per liter as calcium carbonate is due to calcium. So I'll start with that 160 milligrams per liter. So 160 milligrams, and I'm going to use calcium carbonate per liter here. And then I'm going to convert that into grams. So I know that my 1,000 milligrams is equivalent to a gram. And then I'll convert it to moles using the atomic or molecular weight of calcium carbonate. So a mole of calcium carbonate is going to be 100 grams. And then I know now that calcium carbonate is 2 equivalents per mole. Okay. So then, just for this sake, I'm going to be really kind of so for the sake of being overly thorough, okay, I'm going to see that. So an equivalent of calcium carbonate is the same number of equivalents that calcium has. And then I know that there are 2 equivalents per mole of calcium. And I also know that a mole of calcium has 40 grams. And then I want to get to milligrams. So a gram is 1,000 milligrams. And let's go ahead and double check everything so I can cross out those milligrams, cross out those grams, cross out those moles, equivalents of calcium carbonate, equivalents of calcium, moles of calcium, and then now I'm down to milligrams of calcium. And what I end up getting is 64 milligrams per liter of calcium. So here's another example that we have. We have water with a pH of 7, and it's got a certain amount of bicarbonate ion in it, and we're asked what the alkalinity is. So to start off, what we're going to do is we're going to remember that alkalinity equation, where, let's say, alkalinity, I'm just going to write alk in equivalents per liter is equal to the concentration of bicarbonate, and I'm going to just leave out that, 1 equivalent per liter for the sake of fitting everything on one line, plus 2 equivalents per liter times the concentration of carbonate, plus the concentration of hydroxide, minus the concentration of hydrogen ion. Okay, so at first glance, you might say, okay, well, we've got, we know this, and we want to get that. We don't have enough information. But if you think about it a little more, you might realize that, oh, actually, we do have enough information if we make some assumptions. So let's first start with this first assumption is we're going to assume that this carbonate is negligible. If you know a little bit about carbonate species and pH, you will know that that is probably true in our system. And the problem also didn't say anything about carbonate. So, and I have another, or I will have another video about a little more about carbonate speciation relative to pH, if you have some questions about that. So this other, what else can we do? So we know that the pH is 7, right? And so we'll just do a little quick review of pH, right? So we're normally saying, this isn't entirely true, but let's say most chemistry, at least intro chemistry, would tell you that pH ranges from 1 to 14, where 14 is basic and 1 is acidic. And that pH is basically the negative log of the concentration of H plus ions. Okay, so already, if you know the pH, you can use this equation right here to calculate H plus. And we could do that. We could say that H plus equals 10 to the negative pH. But we don't actually have to do that. Because the pH is 7. So, so basically what we can do here is we've got this, this equation for pH, but we can also write a similar equation for pOH, which is the negative log of the hydroxide ion, or OH equals 10 to the negative pOH. And if you'll remember from your chemistry, pOH plus pH equals 14. And that's always going to be true. That's just a property of water. It has to do with the dissociation of water into hydroxide and hydrogen ions. So if you look at this, and I'm not going to actually do all of this math, you could do it on your own, but if you kind of take this relationship, well, you'll take this relationship, you'll see that pOH also equals 7, and eventually you find out, or you'll come to the conclusion that the concentration of OH equals the concentration of H plus, and so those cancel out as well. So we've really simplified our equation here because we've assumed that there is no significant amount of carbonate, and then the OH and H balances. So we have a much simpler alkalinity equation. And so now we can just go and we just need to convert. So we've got 62 milligrams of HCO3 negative per liter. We'll go ahead and convert that into grams. And then we're going to use the molecular weight of bicarbonate. And what we end up getting is going to be 0.001 moles per liter. Okay, but it asked about equivalents per liter. If we go back and look at the charge on bicarbonate, we'll see that the charge is -1. So for bicarbonate, so we'll just multiply that by 1 equivalent per mole for bicarbonate, and we end up with 0.001 equivalents per liter. And we would say that that's also 1 milliequivalent per liter, but the problem asks for equivalents per liter. So there are our 2 example problems. We've got one where we've got this weird unit, milligrams per liter is calcium carbonate, In order to solve that problem, we needed to use the molecular weight of calcium carbonate and the number of equivalents of calcium carbonate to get that into milliequivalents. Then we looked at the mass concentration of calcium by basically taking that milligrams as calcium carbonate per liter and then converting that into milligrams per liter, which is fairly straightforward, but just remember that I could have also asked you about magnesium, which magnesium hardness can also be reported as milligrams per liter as calcium carbonate, which is weird, but true. Okay. And then the last one is using this alkalinity equation. It's a simplified alkalinity equation that really only considers carbonate species and water, but it will work for our purposes here. We made some assumptions about pH. We made an assumption about carbonate, and then we were able to get that into equivalents per liter. So that wraps up our talks on alkalinity, hardness, and equivalents. We also talked a little bit about units like equivalents per liter and milligrams per liter as calcium carbonate. So between this video and the other video on liquid units, you should be pretty well prepared, given your chemistry background as well, to tackle most problems dealing with unit conversions in water.